Hello, my name is Anna Fausta and I would like to give you a short introduction to channel models for wireless sensor networks and how those channel models can be used for deploying sensor networks. So first of all, how do we actually know how far can a sensor node send or receive packets or data? With other words, what is the transmission radius or range of sensor nodes? We have in general two possibilities to solve this problem. We can do it experimentally or we can do it theoretically. Let's first look how to do it experimentally. It's actually straightforward. What you need to do is to have at least two sensor nodes which you put at different distances from each other, preferably in the same environment and in the relatively similar conditions. And you simply measure, for example, the packet reception ratio as shown in this graph. What we can see here clearly is that there is some correlation between the distance and the packet reception ratio, but it's not a straight line and it's not something which below some particular distance you will expect perfect conditions for communications and above that you will expect it not to work at all. So here, for example, we can see that below a distance of approximately 10 to 15 meters, the communication seems to be working fine. However, the packet reception ratio will still be going up and down from packet to packet. And going with higher distances, we also see that approximately after 30 meters, you actually cannot expect too much of your sensor nodes anymore. This experiment has been performed with older hardware, which was working at 868 MHz. And a tiny OS operating system, just for those of you who are more interested in these details. What is, however, important here is that you can use such data in order to use it, for example, for deploying a real sensor node, real sensor networks, and say you have to keep a distance of below 15 meters in order to hope at least for good communication quality. The other possibility is to go to theoretical channel models. What is a channel model? Pretty much given some parameters of the system, like frequency, like the environment itself, the antennas you use, and so on and so forth, you're trying to compute the so-called path loss. Path loss is a combination of properties and impacts, influences on the wireless communication, for example, coming from reflections, attenuation, multipath, diffraction, and many others. And they're summed up together in order to say what is actually the difference between the power of the transmission and the power at the reception. So this connection is given to us by the so-called link budget equation, which combines all of these things together. Here, for example, we have our path loss, the one which we're trying to compute. Here we have the power of the transmission, so the power of the transmitter itself. Here we have the power of the receiver. This is what we are typically trying to compute, but those two are connected, so whatever you manage to compute, it's enough for you. These two here are the so-called gains of the antennas, ones of the receiver and ones of the transmitter. And here, negative, going into the negative impact, we have the losses at both sides, at the transmitter and at the receiver. This equation gives us a very general, basic understanding of what is good for you and what is bad. With other words, the path loss, for example, is bad for you. The smaller the path loss, the better the communication will be. But the path loss depends on the environment and how the signal propagates in this environment. The simplest way to describe this path loss is to use the so-called Freespace model. The Freespace model assumes that there is a transmitter and a receiver. They have line of sight to each other, and there is absolutely no object between them which could do any reflections or diffractions. So this is also called sometimes the freeze equation or log distance path loss because it is based on logarithmically on the distance between the receiver and the transmitter. In general, the equation looks like that. And again, what we see here, what we already know, are the gains of the antennas. Here what we see is the wavelength of the transmission, which is the speed of light divided by the frequency of the transmission. Here we have the very well-known pi, and here we have the distance between the two. And all of them are then combined with this logarithmic scale here, and the path loss can be now computed in terms of dB. However, if there is a kind of a shortcut, if you don't know, for example, the gain of the antennas or the wavelength and so on, you can actually do a combination of experimental and theoretical design here, so that if you have a known path loss for some particular distance d0, which you acquire experimentally, you can revert a little bit the problem and it becomes a little bit easier, because now you can express the path loss or the power at the receiver in terms of this path loss or the power of the receiver at this distance d0. It is important here to note that d has to be bigger than d0. So this is one possibility how to compute, for example, the received power. If you can compute the received power, you can of course compute also the path loss easily. And another way of representing exactly the same equation is again in terms of a logarithmic scale. And here we see something new. And this is this n here. N is the path loss exponent, and it's a kind of a magical constant which depends on the environment itself. For free space, it's defined as 2.0. For other spaces, it can be less or more, depending on how many obstacles and how much interference you actually expect in a particular environment. You can put this information into this path loss exponent. The path loss exponent can be found in the literature, for example, in one of the main books on wireless communications by Rappaport, which is considered one of the main books on this topic. There, for example, you can find a table of some path loss exponents depending on the different environments. Here, for example, you see, as I said also before, the first free space we have a 2. Then for some urban area cellular radius, it's higher. But for example, in building line of sight, it is actually lower even than in free space. This is due to all possible variations in the environment and to the reflections, multipath, and so on in these environments. However, you can also try it yourself experimentally to see whether these path loss exponents actually are correct. And this has been done by colleagues in Portugal, who in 2013 have tried it out in these three environments which you can see here: in free space, in the building, and obstructed in factory. So you see that these three environments are very much different from each other, and at the same time you also see that the setup of how they have measured the path loss exponent is exactly the same. The height is exactly the same, the hardware is oriented in the same way to each other, and so on, and they are in line of sight always. So what they have acquired as results is actually quite interesting. Here you have the results from Rappaport, so exactly which we have seen in the slide before. And here you have their own measurement. So you see that the free space is actually a little bit lower than the 2.0 exactly. That will be, of course, very, very different in another free space, but this is what they have measured. In building line of sight seems to be pretty well described by the original table from the literature. And the environment where you have obstruction in factories, you also see that the free here is not really reached. It's only 2.55. But of course, that depends on how much obstruction actually you have in a factory. So in this case, probably they have less than in some other factory where you will see even more equipment around and even with more reflections and more obstructions. So it is important to keep in mind that whenever you're using this channel model, you actually have to have a good idea of what is the path loss exponent. Otherwise, the results will be very, very different. You see it also from the formula. Another very popular model is the so-called two-ray ground reflection model. Here we are going a little bit one step further in more precisely describing the environment of the signal propagation, and we assume that the transmitter and the receiver are now at different heights. Here we have the transmitter, and here we have the receiver. So they're at different heights. They can be, of course, at the same one, but we have a differentiation between those. And we know that they have a line of sight, which is this line here. Oops. But we also have one reflected wave, so only one. So I will not explain you here how exactly to reach to the calculation itself, and there actually are also many approximations to this equation. One of them, and the simplest one probably, is to compute the path loss in terms again of logarithmic scale, logarithmically from the distance. And here we will have also the gain of both antennas, which is now described as the product of both gains. And here we have the heights of the transmitter and the receiver. So if you compare it to the Freespace model, we quickly figure out that the new component here is really the taking into account also the height of this and, of course, also the secondary wave. If you now try to compare all of these models to each other, you'll pretty quickly see, for example, that the Freespace, which is plotted here with this black line, is kind of a simple line. Please note, however, that we have a logarithmic scale on the x-axis and a normal linear scale on the y-axis. So if I plot this in a normal linear scale, it will not be a line anymore, but it will be an exponential falling function. But in this case, we just see this line because it's in a logarithmic scale. If I now use exactly the same parameters, and I would use for height of the receiver only 2 meters, so it's pretty low above the ground, you will see that the path loss now changes dramatically. You see that some parts are quite similar than before, but especially in the lower distances between the receiver and the transmitter, there are these two bumps here, and at higher distances the path loss becomes much more than it will be predicted by the Freespace. If we increase now the height of the receiver, let's say to 30 meters, then these bumps become many more, but the difference at the so-called long distance become actually less because the antenna is also higher. And then if we further increase the height of the receiver, we actually go even to even more bumps, and you see that the maximum, however, is nicely always exactly the same. So you see that there is a huge difference on which channel model you actually use. There are many more channel models which are taking into account also other more multipath reflections. Some of them are taking more into account, for example, also the humidity of the air and many other properties. However, the basic idea remains always the same, that we're trying to predict the path loss or the power at receiving node in order to predict how far actually sensor nodes can communicate. So how exactly to determine the transmission radius now? We know already that these three things, the power at the transmitter, the power at the receiver, and the path loss, are actually very simply connected to each other. Then I also need to know what is the sensitivity level of my transceiver. For example, it is usually approximately around minus 100 dBm. Then we also know that the maximum transmission power is usually around 0 dBm. Many of the sensor node hardware allows you to program the maximum transmission power, so you have to be careful which one you're actually using. But combining all of this information, it becomes quite simple actually to predict what is the transmission radius. And you have here two possibilities. Either you try to solve this mathematically, if you are well off with such equations and logarithms and so on, you can do that mathematically. The other possibility is just to plot, for example, the path loss for different distances at small intervals, and then to see where the path loss exceeds the sensitivity level, or the difference between the sensitivity level and the transmission power. And there you know that there you cannot send further than this particular distance. These are the two possibilities here. So in summary, what is important really to remember also is that channel models are typically very optimistic about the path loss. With other words, they would predict a much longer transmission range than you would encounter in reality. In reality, it depends on too many things around. What are the obstacles around? How much humidity you have in the air? Whether somebody is moving around or not, whether you're closing or opening windows and so on. So all of these, especially the simpler the channel model is, the more optimistic it will be about the transmission range. That's it for today about channel models. Thank you very much.